What's ahead is out there beyond the horizon, but some of us can see it. We can see a world where automobile accidents are a thing of the past, because cars can think for themselves. We can see a world without climate What's ahead is out there beyond the horizon, but some of us can see it. We can see a world where automobile accidents are a thing of the past, because cars can think for themselves. We can see a world without climate change, a world powered by the sun and the wind and the waves. We can see a world where doctors predict disease before it occurs, using virtual models of the human body. We can see a world connected as one community, thanks to communication networks accessible to all. At ANSYS, we can see exactly what the future brings, or rather, what we bring to the future. Through the power of simulation, we are enabling innovators to create this new world for everyone. Only then can we engineer what's ahead. What's ahead is out there beyond the horizon.
And it's not recording.
Good afternoon, ladies and gentlemen. Welcome to the webinar on stimulation-driven vehicle lightweighting for efficient and sustainable mobility. I'm Suraj from SA India, and once again, I welcome you all to this wonderful webinar. This webinar focuses mainly on vehicle lightweighting. Reducing the weight of a vehicle is one of the important focus areas for the automotive industry to control fuel expenditures and limit emissions. Increasing focus on sustainability at advanced materials offer great potential to improve vehicle efficiency, as it takes less power to accelerate a lighter object than a heavier one. A 10% reduction in vehicle weight can result in an average of 6 to 8% fuel economy improvement. Simulation plays a key role in helping industry adapt to lightweighting and come up with future-ready designs to maximize the performance on both fronts, fuel efficiency and emissions. Just to highlight an example, using simulation, weight of transmission crossbeam can be reduced by up to 45%. So in this webinar, you're going to learn about advanced materials on the selection and validation, how to optimize those, the techniques involved like on parametrics and gradient based, the topology optimization on additive manufacturing, the parametric optimization, and case studies. So for that, we have a special expert speaker with an experience of 11 years in modeling and simulation and 7 years with ANSYS. His expertise is on vehicle lightweighting, reduced order modeling and digital twin, and non-linear simulations. He's a MTech from IIT Kanpur, and we extend a warm welcome to Gaurav, and the stage is yours now, Gaurav. Please go ahead.
Yeah, thank you, Suraj. I hope I'm audible.
Yep, loud and clear.
Okay. Good afternoon, all, and welcome to this session. Thanks to SA for providing me this opportunity to come out here and interact with you all through this platform. Let me start by sharing my screen. So, Suraj, can you please confirm if my presentation is visible?
Yeah, presentation is visible. Yeah, it's good. Can you just
Okay, great.
excuse me? Yeah, can you just duplicate the slide? It's just on the presenter view there. You could just it's a display settings
Okay,
on. Yeah.
sure. All good?
Yeah. Now it's good.
Okay, so welcome again. Welcome to everyone. As Suraj mentioned, this is Gaurav Sharma from ANSYS India Private Limited. And today in this session, I'll be talking about simulation driven vehicle light weighing. So for the agenda, the light weighing that we are going to talk about is primarily based on three pillars. One, topology optimization. The second is parametric optimization. And third one is the advanced materials. But before we start, I would like to introduce my organization. So ANSYS was founded in 1970 and we started off with mechanical solver. In the past 2 decades, with an investment of around $4 billion, we acquired 24 companies. And now within our portfolio, we have solvers that are based on physics coming from either fluid, structural, EMAC, or thermal. Other than these acquisitions, we also have partnership with technology enablers like Microsoft, SAP, PTC that provide us IoT platforms which we use for building twins. As of now, we are a team of around 5,000 engineers, 5,000 professionals around the globe. With this, let me move on to the topic of the day, light weighing. So the first question is, why light weighing? Why do we need it? As was mentioned in the introductory note, the primary reason that pushes us towards light weighing is the rising fuel cost. With rising fuel cost, there is a need to come up with vehicles which are more fuel efficient. On top of that, with the advancements in the field of hybrid and electrical vehicles, there is an ever increasing need to penalize for the additional weight that comes along with the components such as batteries. And not to forget, the next generation emission targets are more stringent and light weighing is important from that aspect as well. So we'll talk about the first pillar of light weighing, which is topology optimization. What is topology optimization? Topology optimization is a process that uses a physics-driven approach to work out where to remove material from a block in order to get the most efficient or the optimized shape based on certain constraints. So it talks about a physics driven approach. This means it starts from a simulation that mimics the physics of the application quite well. On top of that, this topology optimization studies build upon. Now, topology optimization comes in as an integrated module along with our workbench platform. Now we'll see how it integrates with the existing static structural analysis using an example of journal bearing. Here's a bearing, and I wanted to know what is the scope of material removal in this bearing. To make a start, we perform a static structural analysis, and as I was mentioning on the workbench page, we can seamlessly integrate the topology optimization module along with the static structural one as shown in this image. Now it's fairly easy to use and seamless workflow. And now we'll see what are the broad steps that are required to perform this topology optimization study. It starts with the static structural analysis. In this example, in this case, the static structural can be replaced by a modal analysis as well if the frequencies are of interest, or a thermal analysis as well. But for this demonstration or for this example, I'm using static structural. Now this study starts with a static structural analysis, which requires coming up with a mesh, then applying structural loads and boundary conditions and solving the structural analysis. Once the structural analysis is solved, we move on to the topology optimization part, where we define certain objectives and constraints. For a light weighing exercise, more often than not, this objective is either mass or volume. We want to either minimize the mass or we want to either minimize the volume, keeping certain constraints in mind. These constraints can be stresses, deformation, stiffness, etc. Once we have completed this topology optimization study, the outcome of this study is the optimized shape, such as the one shown here. Is that the end of road? No, we have to validate how this optimized design is going to respond to the loads and the boundary conditions that this component is going to be subjected to. For this, we perform some basic CAD operations such as smoothing and generate this geometry back, on which we reapply boundary conditions and load, perform a validation study, and get the numbers of interest such as stresses, deformations, etc. So these are the few steps which are required to complete a topology optimization study. And I was mentioning this integrates well with static structural, thermal, and modal analysis systems. And all the steps which have been shown here are quite easy to use using the Workbench platform. For this particular case, let's look at the numbers that we have got after optimizing this. Sorry, someone is saying something? Okay. So here are the results. This was the.
You please go ahead. There's no distance. You can please go ahead.
Sure. So this is the geometry we started with, and this is our optimized geometry. The initial weight was around 342 grams and the final weight is 151 grams. There's a hefty weight saving of around 55%. But definitely this comes at a cost. The cost is the equivalent stress, which was earlier at 21.8 megapascal, is now 196 megapascal. And the maximum deformation is now 0.1 millimeter. But as long as these numbers remain within our prescribed limits, we are all set to go. This study indicates that this bearing, which was kind of over designed, is now optimized, and this would be my go-to design, which would fulfill all my requirements with an additional 55% saving on weight. Okay, now having understood what are the steps involved and what kind of results do we get out of optimization or topology optimization, a curious question is what goes inside, what goes under the hood. So I'll just take you through the algorithm. I'll just take you through the algorithm of how this topology optimization functions. What is the mathematics behind it? For any typical optimization problem, there are broadly three things needed. One thing is a design variable. It is a variable on which the solver iterates and is trying to find an optimum value of this variable. Second thing is an objective function, and the third thing is a constraint function. So mathematically, program is trying to minimize or maximize the objective function by iterating on the design variable such that the constraint is not violated. So this is for a general optimization problem. Now coming to topology optimization in particular, in topology optimization, the design variable is a pseudo density function, and this pseudo density can vary anywhere between 0 to 1. What does 0 means? 0 means the density of a particular element would be, or the pseudo density of a particular element would be considered as 0, which indicates the existence of this particular element is not, or the existence is kind of redundant. We can drop this element. But if the pseudo density is selected as 1, that means this particular element would be retained for this analysis. Objective function for a topology optimization study is definitely going to be mass, and then we can have a number of constraint functions that can be stress, deformation, or manufacturing criteria. Basically, the problem definition goes like the optimizer functions in a way that the design is modified by varying these pseudo density values in FE mesh. So at each element it goes and it tries to see that whether the presence of this element is required or not. If it is not required, it will drop the element by assigning it a value of 0. It is required, it will keep the element, and this is how it keeps on iterating and try to meet the objective, keeping in mind that the constraints do not get violated at any stage. By dropping an element, if the constraint is violated, it will take a step back and it will make sure that the element is retained. So broadly, this is how the algorithm functions. Now let us look at some types of optimization. Within topology optimization, there are broadly three categories. One is what we have already seen, topology optimization. The entire topology is modified. The second one is lattice optimization. In lattice optimization, the external shape of the geometry is retained, and we do see the geometry being idealized using lattice structures. The third one, just for the sake of completeness, is shape optimization. This is not a mass optimization algorithm, but it functions by morphing the nodes and is beneficial in redistributing the stresses at the critical locations. So for the sake of this discussion, we'll be focusing only on topology and lattice optimization, which are the algorithms aimed at mass optimization, mass reduction. Let's take a look at one of the application examples of a knuckle. Now here I have a knuckle that I want to take through the scissor, and I want to reduce mass out of it. In order to do so, as I was mentioning earlier, we need to perform a static structural analysis. For doing so, we want to understand what are the different loads which are going to come on this knuckle. If that information is available, well and good. If it is not, sometimes we may have to perform an RBD study, and from where we can get the information about what are the different loads which are going to come onto this knuckle, and then we perform a static simulation using those loads and boundary conditions. Once that is done, we have two different mathematical approaches for the Topology optimization. The density-based approach is what I was explaining in a previous slide. That's a mature 30-year-old technology, but we now also have a level-based approach, which is relatively new, and it works better for most of the complex load scenarios. But eventually, if you can see in both of these images, the optimized shape looks fairly similar to each other. There's not much difference in the optimized shape. Eventually, they take us to same results, but through a different route, through a different mathematics that is involved. Next, we'll have a look at another example of algo bracket, which works with lattice optimization. Now, this is a bracket which I want to reduce the weight of. For this application, I do not want to change the outer shape of this particular component of this particular design. So what we do is we put it through lattice optimization. In lattice optimization, the solid material is substituted by beam structures depending on the FE calculations, and this is the kind of a structure we eventually get. Now the problem that arises here is with respect to validating this optimized geometry. The optimized geometry is highly complex and the material is highly discontinuous. The mesh that I will have to need for this structure would be huge, and so would be the computation time. So the validation becomes challenging, and that is the reason we have introduced approach based on knockdown factors, where we do not have to actually take this optimized shape into a validation study, but based on the knockdown factors, we can take this particular shape only to a validation study. You can see over this. So after performing this topology optimization study, the validation was performed not on this geometry, but on this geometry. But the effect of this lattice was taken into consideration using the knockdown factors. So this makes our life very easy when it comes to validation. But alternatively, if one needs, we can also generate this design, this geometry through back to cat operations using some basic geometry operations. So the point to highlight here was that the validation that is being performed using knockdown factors make it much more easy and fast to analyze the optimized design that is coming from lattice optimization. Okay, so we have seen these couple of cases. Now let's look at the results we get for this. This was the optimized shape of the knuckle. The initial weight was 14 kgs and the optimized geometry had a weight of 8 kgs, a hefty saving of around 55%. And due to the elimination of stress concentration region, the stress is also observed to have reduced from 225 to 205 megapascal. For the lattice optimization bracket study, the weight is reduced by 52%, but it is coming at definitely with the reduction of weight, the stiffness has also reduced. So this displacement is increasing. It has moved up from 1.17 to 2.15 mm, but as long as this is within our prescribed limit, all is well. Now, the third study that I did not go into the details of was with this manifold, and we can see that this was aimed at redistributing the stresses, and the stress distribution got improved by 32 and 12% after this study. So this is broadly what I wanted to capture on topology optimization. Now, topology optimization definitely remains one of the most critical, most useful tool when it comes to light weighing, because it is easy to use and because it is fairly automated. We just have to provide some boundary conditions, constraints, and objective at the GUI level, and the solver takes care of the rest of the things. But the problem is, what if I am dealing with a situation which is more complex? What if I have multiple objectives and not just mass reduction? And things can become more complex if these objectives are contradicting. So there would be a situation where a trade-off has to be done. What if I am exposed to such scenarios? Then what if I am dealing with a physics which is something other than thermal, modal, or static structural, because topology optimization works only in conjunction with these three analysis systems. These are the cases where I might need more insight to my problem. I need to I need to dive deeper into my optimization study. I want to witness what trade-offs are going on. I want to take a decision on the trade-offs. So for such cases, one such example that I can think of is a rotor study. A brake rotor is something that I do not just want to remove the mass, but the deformations are also important. The noise levels are also important. Emissions, appearance is also important. So there are quite a few of parameters which are important to us. There are quite a few of objectives that I have to deal with, and not just the mass. Mass is one of the important objective, but I also have to ensure that other objectives are also fulfilled. And if there are contradicting objectives, I want to understand what the trade-off is, and I want to make a final statement on what trade-off I am okay to go ahead with. So for such cases, parametric optimization offers a great solution. And this brings me to the second pillar of light weighing, which I mentioned as parametric optimization. Now, ANSYS offers solutions like OptiSlang, which helps us perform a parametric study. It says that there are 4 stages that leads to a robust design. Stage 1 is model calibration. Again, this is driven by simulation. The starting point of all this parametric study is a simulation that mimics the physics of our application. Going down the line, we'll be performing a design of experiment study. It would need some good amount of solver runs, 20, 50, or sometimes 100. So there is going to be an investment in terms of computational time and resources. Now, before we go on and make that investment at this stage, it is important for us to establish that the CA model that I'm using mimics the laboratory condition well. So that is being taken care of at this stage, which we call model calibration. Any unidentified parameters, for instance, any material properties, we perform the regression analysis and we make sure that the model we have is well calibrated with the laboratory before we move ahead. Stage 2 is design understanding, which we also call as sensitivity. At this stage, we try to see how sensitive is our design to different parameters. What happens if I tweak certain parameters? How is my design going to behave? These certain parameters can be geometry based parameters, especially when we are talking for light weighing. We want to remove some mass, and that's when the geometry based parameters comes into picture. But since we are also talking about performance, these can be performance based parameters. These can be certain loads as well. So at this stage, we try to understand how my design behaves if I tweak a certain parameters. And once this design behavior is known within the design space, the next stage is about design improvement. What is the optimum operating point for my design? What is the point? What are the input conditions that would lead to minimize mass along with other objectives? And the fourth stage is called design quality or the robustness study. At this stage, what happens? We try to answer that, okay, I've got a optimized geometry, optimized design, but is my design capable of handling the uncertainties that it will be exposed to in field? These uncertainties can be in terms of variations coming from material properties, variations coming from loading conditions, or the geometric tolerances. So we have to answer that whether my design is capable of handling all these variations. Now, in the current context, when we are talking about light weighing, model calibration and design qualities are not that significant. What we are going to focus on is design understanding or sensitivity study and design improvement. So the first stage for light weighing becomes sensitivity study, sensitivity analysis. This means at this stage, I want to understand what happens with my design if I change a certain parameter. So what goes in as an input to this sensitivity study is the outcome of a parametric study or a design of experiment study which needs a number of solver runs. So I have identified parameters that are critical, that I assume to be critical for my uh, application or for my design, and I want to change these parameters within a certain range. So this range defines a parametric space or a design space, and now I want to understand how my design is going to behave within this design space. So the outcome of a sensitivity study is such meta models which is shown here. This meta model is nothing but a mathematical relation which is being plotted on a 3D plot between the output and input. So it tells us how my output is going to vary if I change certain input conditions. On top of that, the output of sensitivity studies also parameter importance. It tells us out of all the parameters we assumed, which parameters are critical for a given objective. So I might have used 5 or 6 dimensions, and then the parameter importance will show that, okay, you have chosen diameter of this particular hole as a dimension. It is important when it comes to the mass of this component, but the radius of the fillet, a small fillet that you might have chosen as a diameter or as a dimension or as a parameter, is not that relevant. So all that sort of answers all those kind of insights into my design I get at this stage. Now this sets the ground for me to understand what kind of decisions can I make with the current or existing design. What are the possibilities? What kind of dimensions I can change? Is changing this dimension going to have significant effect on the mass of this particular application? If yes, does it have any deteriorating effect on any other output parameter? And then the trade-offs comes into picture. This also sets the ground for optimization that I'm going to discuss in next slide. Once we have these meta models available, these meta models are essentially an image of what all can possibly happen, or what all can possibly this design do for me within the design space. Now, when we talk about mass, often the optimization point is a minimum point. So the next question is what we do with optimization in terms of light weighing. Once the variation of mass with different parameters is known, we want to get to a point where we are talking about minimization of mass. So there are two ways we can attain this. On the meta model, the optimization can be performed, which we call as indirect optimization. If my response surface of the meta model is such as this, which is not very highly nonlinear, we can perform this optimization on the meta model itself, and I'll get to the point where the mass is minimized. The problem here is when the meta models get complex and when the meta models gets very highly nonlinear, such as this one, what happens then? There are so many local minimas over there. For such cases, this optimization on meta model or indirect optimization may not yield best results. So we do have approaches which are called direct optimization. We do have those algorithms which will help us deal with such highly nonlinear cases as well. The bargain is optimization on meta model is fairly quick, hardly takes a minute or two, and it just requires one additional solver run that is performed on the optimized value in terms of validating that whatever we were predicting is correct or not. However, the direct optimization that needs quite a bit of additional solver runs, and definitely it has its own, it has an impact on the solution time in that case. Now, for the case of mass optimization, all this is well, but another important aspect that we need to understand here is the trade-off that I was mentioning earlier. What if I have two different objectives, let us say mass and deflection, and I want to minimize mass, but I also want to minimize deflection. Now, these two are contradictory in nature. It is not possible to attain both of them simultaneously. If I'm going to remove mass, stiffness is going to come down, and for the same loading conditions, the deflections are going to be high. So we do come up with this Pareto charts which are shown over here. The two, the x-axis is one objective and the y-axis another objective. Let us say I have mass on x-axis and I have deflection on y-axis. Having generated these meta models, I can now extract thousands of possible design points and plot them on this Pareto front in a fraction of minute. I do not need any extra solver runs. And that gives me the power to perform this Pareto study and do this trade-off. On this Pareto front now, on this Pareto chart now, this becomes my Pareto front. These are the design points which are relevant or important to me. And one of these design point I have to select based on the kind of trade-off I want to go ahead with. So if F2 is my mass, I want to minimize mass, but I would say that, okay, maybe at B is something that I have to stop, because if I go beyond this, the deflections are going to improve drastically. And I do not want to go ahead with such high deflections. So this is just one example, but I think we are able to relate now how these Pareto fronts and Pareto charts are useful when it comes to multi-objective, multidisciplinary optimization. So we'll take a pause and I'll just share this case study of a brake rotor, wherein we'll see what kind of trade-offs we have to do when there are multiple objectives. So this is again the same rotor problem, and we'll see what kind of trade-offs goes in when we are optimizing with mass on one side and other performance related parameters on the other side. When it comes to performance related parameters for this particular application of rotor brake, conning is one parameter which is of importance. Under the effect of thermomechanical loads, there are these sort of deflections that comes into pictures, and they have an adverse effect on brake torque variation. So conning is one aspect of performance, and the other aspect of performance is high stresses at some of these locations coming at the time of deceleration. So both these characteristics needs to be evaluated in a rotor design along with the mass optimization. Now when we go for a mass optimization problem, we have a design space. In order to retain the functionality of the rotor, we cannot play with any geometric parameter in the red zones. All we are left with is the green zone. Now, when we are trying to improve the performance by making some changes at this region, definitely we can add a lot of mass over here and the coning will go away. The stresses might also get better, but then the mass optimization comes into pictures. We need to have a limit on that. So there are an n number of design ideas. I may play around with the configuration around this region. I can come up with something like this or something like this, but I'm really not sure what it's going to, what's the effect going to be on coning and the deflection and the stresses along with the mass. So the way to go ahead is create a parameter, identify the relevant parameters and create a parameter space. What I've done here is I have gone through this narrow region and I have defined 8 different parameters that will completely govern the shape and size around this region. And I have associated a range to these parameters. This becomes my input parameters. On the output side, I have 4 parameters: stresses at these 2 critical locations, mass of the design, and the coning angle. Now I perform a design of experiment study followed by a sensitivity analysis. So what this sensitivity analysis gives me as an output is these kind of meta models. These are the governing equations. So these tells me how my any output is going to change if I change a particular input condition. Now the problem for me is, let us say for coning angle, this becomes my optimized point. So these corresponding input conditions I would like to freeze, but unfortunately I can see that these input conditions have a drastically adverse effect on the mass of the design. So I may not necessarily live with this particular condition. I have to make a trade-off. I have to do some relaxation on coning in just to make sure that the mass of the application does not go beyond what it is currently. So that sort of trade-off is again done at the Pareto front end. As I was mentioning, once these meta models are available to us based on say 20 or 30 solver runs, now I can extract thousands of design points from these meta models without having to perform any single extra run within a fraction of minute. So these Pareto fronts are developed, these Pareto charts are developed within a fraction of seconds. Using this Pareto chart, on the x-axis I have mass of rotor, and the y-axis I have one by one I'll put rest of the parameters, and this red line becomes my Pareto front. On this front I will pick one particular design that would make most appeal to me. This would be my decision. In this case, the optimized design looks something like this. And when it comes to performance parameters, the mechanical strength indicator or the stresses at region 1 came down by 19%. Region 2, the stresses came down by 25%, and the coning deflections came down by 27% compared to initial design, whereas no significant increase in mass was observed because of these changes. So this becomes a solution of my optimization study in this case, where there are multiple objectives which are in conflict with each other. Okay, so having discussed the topology optimization and parametric optimization, this brings me to the last segment of this presentation, which talks about light weighing through using advanced materials, or as we'll see, alternate materials. Now in the current setup, our material selection process is usually governed by what we are used to, what we are already using, or what are the company's preferred materials, or whatever materials are being supplied to us by the vendors and suppliers. And for the identifying the material properties, we have a lot of resources. We can even do a web browsing and identify what are the material parameters, material properties for a corresponding material. But simultaneously, the material technology has seen advancements, and we now have materials available which may have same structural performance compared to our traditional materials, but may be less dense or may have less weight compared to the traditional materials. The question is how to identify those materials, how to reach them. Our current database may or may not have information on those materials. Sometimes people do such exploration in silos. There are different teams in an organization, the design team, the simulation team. In simulation teams, again, there are many teams, and we work on silos and we try to answer these questions, and all the explorations we performed, whatever we identify, remains in silos. So we do not have a global repository or a universal repository which we can look for. For this, ANSYS offers a solution in terms of ANSYS Granta MI, which is a gold source for corporate material intelligence. It consists of, it can consist of all the proprietary information in terms of material that might be available within an organization. This proprietary information can come from CAE models, laboratory testings, or a comprehensive library based on existing data in terms of some data is coming from assembly or different libraries that people might be referring to. So all these informations which might be locally available within an organization can go into Granta MI, and this becomes a repository. As of now, I'm just talking about a repository. In subsequent slides, we'll talk about once we have a universal repository which has all sort of material data available, how can we use it through Granta Selector in order to come to an alternate material. So with Granta MI, it has that repository. We also have this tool called Granta Selector. Granta Selector has its own material database and material properties, and along with the information that we got from Granta MI, the local material data that might be available with any organization, we come up with a large of material information. Okay, and this is one snapshot that is being taken from Granta Selector. You can see on the x-axis we have density, and the y-axis we have Young's modulus. Now these can be any material properties. Definitely for light weighing, we keep density at x-axis, and the y-axis can be any particular material property of importance. What we need to do is, for a given Young's modulus, we can see there are so many alternate materials available. Each point on this pool is a material. On the this side we have metals and alloys, on the center we have composite, and here we have plastics. So we can see that for a given Young's modulus, what all different class of materials and what particular materials is something that I can use of. This sort of information can be extracted from these charts. Now, Granta Selector is an encyclopedia of material data. We have our own material database, and the locally available material information can also be fetched into this pool. And it's a powerful visualization, filtering and solving tool. We'll see that how that filtering takes place in next slide through an example. And then any material that we identify as an alternate material, suppose we started from here and we saw that, okay, this becomes our alternate material. I can just reduce the density without any compromise on Young's modulus. If I narrow down on this material, I can just click on this, right click, and export it to be used for any CAD or CAE operation. So this helps us find similar materials. On the y-axis, we can have some material property, existing material property, or we can also create some user-defined properties. This integrates well with ANSYS Workbench, and the core benefits remains it innovates through materials, quickly resolve material issues, identify alternate materials, confirm and validate choice of materials, and reduce cost of materials. So the x-axis can also be a cost of material. For the sake of simplicity, let me start with an example where the cost of material is important. So I have this component which is made up of PS66 with 30% GF. This is a composite. So I'm plotting to begin with all polymers which are available in the library. So here are all the polymers which are plotted here. Because cost is important for this study, so I put cost on the x-axis, and flexural modulus is something that I do not want to compromise on. It's being put on y-axis. Now my current material lies somewhere here. If I move horizontally from here, there is a large range of materials that are available that can be used as alternate materials. Some of, for same flexural modulus. Definitely, if I move in the positive direction, these would be costlier materials. If I move in the negative direction, I'll get materials which would be relatively cheaper. Now, this is still a large pool of material. What I can do is I can add further filters, further criteria, such as I only want to go ahead with materials which can be manufactured using injection molding. That might be another constraint or criteria that I have to respect. And we can see we have narrowed down further. Some of the materials have further grayed down. I can use few more criteria or few more filters that would be there on my mind, or that is something that I have to respect, such as I want to have a filter on stiffness and impact and moisture absorption. I do not just want to have a cheaper material. I just want to make sure that is moisture absorption is comparable to my existing material. So once I put on those filters, it narrows down further for me. And at this stage, I can see that this was my existing material. When it comes to lower cost, I have three more options available with me. So optimal candidates become PP 50% LGF, 30% GF, and PBT 40% long GF. So that is how the exercise goes when we talk about finding an alternate material using Granta Selector. So we talked about creating a repository. Granta MI has a role to play when it comes to integrating the locally available material data along with what is available within Granta Selector. And once we are within the Granta Selector, we can perform such exercise using Granta Selector. Next, we have some examples here. This is a steering rod, which is made up of steel. we have this turbocharger housing made up of brass and this dashboard made up of ABS. I want to perform light weighing here. I want to identify alternate materials that may have same performance correspond compared to what we are using currently, but they have to be lighter in weight. So in order to proceed, I would first identify what are going to be my parameters of importance or the filters that I would.
Hello, Gaurav. Actually, you're not audible right now. Uh, Hello, Gaurav. You're not audible still.
Hello?
Oh, yeah, now it's audible. Can you just come from the start? I think we lost you from the first material itself. You know, the audio
Okay.
was not.
So should I go back, Suraj? Which
Yeah,
at what
yeah.
stage?
From the first material itself. From the first material, you can start.
Okay, so on this slide only, right?
Yes, see on the slide on the from the first material. Yes.
Okay, sure. I'll go back a bit. All right. So all I was saying is, before we go and use the Granta selector to find alternate materials, we have to list down what are our requirement when it comes to the application of this material. And this often has to be looked in conjunction with what application we are dealing with. For the steering rod, it should have adequate stiffness. The operating conditions are -40 to 225 degrees Celsius. It has to be resistant to salt water. That is again coming from the application. It must avoid resonance and it should be made up of material which can go under mass production. On the housing side, again, we have some similar parameters listed that are important for this application, and that would be useful when we'll be trying to identify an alternate material. These would be the filters that I'd be using. And similarly for the dashboard, it should have high toughness, durable to environment. The temperature range should be -20 to 105 degrees Celsius, and it should be manufacturable by near shape processes. Okay, so with these objectives, I went through the similar exercise using Granta Selector, and I've come up with alternate materials or the materials which have similar performance but are lighter in weight. So for the steering rod, we have carbon reinforced BMI, which is 75% weight saving, PPS 60% glass fiber, which is 60% weight reduction, and for ABS we have PP 20%, which is 35% lower cost. Now this looks very aggressive. I mean, this looks wonderful, great, 75%, 60%, 35%, great numbers. But we also need to validate what we are going to do. See, because we started off with something which was made up of steel. Now we are talking about fiber reinforced plastics here, right? So the failure modes might have changed, and we also need to take one extra step in order to validate what is going to happen if I make the change of material from steel to, let us say, carbon reinforced BMI. In order to do that, a simplified step can be coming up with idealized geometries and performing simple solutions over there, simple simulations over there. So for this steering rod, this can be idealized by something which looks like this, and this is predominantly going to function under torsion. And for the rest of the two applications, we can come up with something like a plate, which is just going through bending. And then we can use the new material properties and try to see how these idealized geometries are going to behave. We have to ensure that there is nothing we are going to missing once we make this change from traditional material to the reinforced materials. Now this is still easier said than done. While for the light weighing aspect, this looks good, this is fine, but it has still an aspect to it which comes to thorough validation. Now, most of the cases we saw, these were the resultant material was something which is short fiber reinforced plastics, and these can have different failure modes. So at this stage, we want to take it one step ahead and perform a thorough validation using simulation. I'm not going into the details of that thorough validation. That opens an all new topic of how these short fiber reinforced plastics can be put through simulation. But it is important at this point, while we're talking about light weighing, we also should mention that a validation is important. Whatever corresponding alternate material we have identified, we have to put it through validation. Just I'll flash a single slide. It is an entirely broad topic, and it's something that we can have another round of discussion. But at this moment, in the context of this particular session, I'll just highlight this slide and try to explain that what are the different stages that goes on into such validation. So if I have a fiber reinforced plastic, stage one would be performing an injection molding exercise that will tell me how the fibers are actually oriented. So we have this injection molding data module that can pull in data from any supported sources listed here. Stage two is identifying what the orthotropic material properties are going to be for a particular fiber orientation. And we have this material designer module here, which can in-house do this exercise, this regression analysis, come up with a DOE, and for different fiber orientation, it will tell us what are the different orthotropic material properties going to be. Now with these inputs, we can perform an FE study. For each element, it will identify what is the fiber orientation coming from here. And for that particular orientation, what is the material property of each element that would come from here. And then we can perform a detailed simulation, static structural or whatever simulation we want to do, and get the results, do a thorough post-processing and validate our material data. So this usually all this exercise we did for Granta is a stepping stone for these sort of exercises. We are not going into the details of these exercises, but having discussed topology optimization, parametric optimization, and how to identify alternate advanced materials using Granta, I would like to park here. Thank you everyone for being with me. Over to you, Suraj. This was all from my side. I hope we do have some time remaining for taking some
Yeah.
questions, right?
Yes. So thank you, Gaurav, once again. It was a really good presentation, and took us through local corners of vehicle lightweighting and even into taking materials into consideration. Thank you very much. And ladies and gentlemen, the attendees, before we go into the Q&A, we just want just a minute of your time for a short, very short poll survey. Just a minute. So we're opening the polls right now. You could answer that, and then straight away we could get into the Q&A session. So we request you to just spend a minute on that, and we'll go to the Q&A session. So we've started the polls right now. So we'll clock 60 seconds, and we'll go into the Q&A. So please go ahead. We just have 20 seconds left on the polls, and we'll go ahead with the Q&A. Yeah. Okay, great. Now we can move on to the question answers. We've enabled the attendees to unmute themselves. So you can take it one by one. You can unmute yourself and ask the questions directly to Gaurav, and he'll be happy to answer. Please go ahead. In the meanwhile, even Gaurav, if you see any questions in the chat box also, you could take them one by one. If not, we'll ask the attendees also to unmute themselves, and if they have any questions, they could clear it.
Okay, let me see if we have something on the chat. So one question is, what about reliability of this design? So this came in at 314. Reliability of the design, I think this was in context with optimization studies. This must be in context with the bracket study we saw. See, for the reliability of the design that was covered in the second half, reliability is governed from parametric study, right? So anyways, we have this optimized geometry, whatever dimensions we are kind of freezing on, there would be some tolerances. And the initial design has its own set of tolerances. The optimized design has its own set of tolerances. With this new set of tolerances, we need to perform a optimize or reliability study on the on this design. Yeah.
Okay. We do have one
Hello.
more.
So this was Arun. Yeah. Yeah.
Yeah, am I audible?
Yes, please go on.
Yeah, sir. Chandresh this side. I have a query regarding the topology optimization and design optimization about sheet metal parts. Do you have some examples for sheet metal part as well? Because the parts which you have shown were kind of forging parts or the casting parts. So for sheet metal also, is this applicable or like not
See,
applicable?
topology optimization, when we talk about sheet metal parts, I believe in terms of simulation, you're talking about modeling them
Yes.
using shells.
Yes.
We do have those approaches. In fact, if I
Do you have any example right
you,
now? Can you
you can
share?
write to me right now, that it would be difficult for me, but you can anyways write to me, and we can share those examples. I'll figure out something for the repository. But since because we are doing it day in and day out, I don't think it's something that we do not have an example. Or maybe I'll just quickly see if I have something. I remember something if I have on locally on my machine. Give me a moment. Huh?
Yeah, please.
By the time if someone else wants to fire another question, that's okay. Okay, Chandesh, so I have this short example that I can show you. You can see my screen, right?
Yeah, it's visible.
Okay, so then idea is to get a design which is of a gripper like this, and before performing a topology optimization on a 3D, usually whenever possible, I try to go ahead with a simplified shell approximation first, and then I make it 3D because sometimes they are time consuming studies. So this is the one that I performed using this shell body, applied loads and boundary conditions and whatever it is, and the kind of optimized structure I got was looks something like this on the shell side. This gave me the confidence that while we are chasing a design like this becomes my this is the design I'm getting from optimization, and this is the 3D design that we are chasing. So now with this design, I can freeze on my loads and boundary conditions and my approach, and I can move on to a 3D analysis and perform a final analysis in order to get something like this. So these sort of studies we do kind of day in and day out. So it works well with Shell.
Okay, and was there any weight saving in this also?
This was not exactly designed for weight saving. Let me tell you very honestly, this was a different exercise altogether. We did it for a concept establishment. If you see that this was started from, I mean, this was started from something very raw. This is a starting point here, right? And this is eventually the final point. Usually the weight reduction studies start from an initial design and they take us to a final design. But this was for concept generation. I might be going into a direction where I'll hit some confidentiality, so I won't be speaking too much.
Understood.
But this is how it is. Yeah.
Yeah, okay. Thank you.
So thank you.
This is Sandeep here from John Deere. I have a question
Hi.
regarding the DOE which you have done. So, is that parameter on the DOE, right? So, is that manually you have to change every parameter and do the run, or is it like automated?
See, once we identify a initial parameter,
Mm-hmm.
okay. So my initial dimension, I had a hole, and the initial diameter of this hole was say 10 mm.
Okay. Mm-hmm.
Now, if I go ahead with optimization, automatically the program will take 20% variation in this dimension. It will try to analyze it from 8 mm to 12 mm. The initial dimension is 10 mm. Automatically, it will take 20% this side and that side. See,
Okay.
for the sake of proceeding, it is well, fine, great. We have something, we are not stuck. I'm using the tool for the first time and I'm not stuck, I'm going ahead. But the sake of having a control on what is going on, this is not great. I mean, usually based on my experience, I will understand, okay, this is a certain dimension and the scope of change that I have on this dimension is from this to this. If I'll go beyond this, it will start interacting with something else. I cannot go beyond this. So usually the range of variation is something which an engineer decides. And this comes from his experience with the current application.
Okay. Okay.
Same goes with loading, right? If I'm doing any further parametric study, you guys might have done a parametric study using Workbench. I have a pressure boundary condition. It is 1000 megapascal. I want to change this pressure. I mean, it depends on how the application is performing. What is the peak pressure that comes into picture when things malfunction? It can be 2000 megapascal.
Mm-hmm.
That is what our testing team or for the field data might have revealed. So what's the point of having 20% variation only? So this 20% variation is just just something, an enabler that doesn't restrict someone from moving ahead if he doesn't have an information on a particular data. But usually for most practical purposes, the designers or the engineers take a call on they create the design space within which they want to understand the design. And this design space is created by the parameter range.
Okay. Yeah.
The floor is open for another couple of minutes. If no questions, we could close, but we do have a couple of minutes, so participants can unmute themselves and ask their or post their questions to Gaurav.
There are many questions in the chat box.
So I'm reading a question by Arun, and Arun is asking how many cycles will this last? So again, this must be in context of some particular application. Arun, if I talk about uh, fatigue life in terms of topology optimization study, fatigue life doesn't reflect anywhere right away. But I can do these back calculations from fatigue life of my component and what becomes my allowable stress limit, right? Using that particular allowable, so if my peak stresses are varying from 100 megapascal to minus 100 megapascal, that means my fatigue life is there of say 80,000 cycles. That is not acceptable to me. So I want to reduce my stresses, but then I see that if the stresses are 80 megapascal to minus 80 megapascal, now fatigue life is more than 1 million. I am okay with this. So that now this particular stress value becomes my constraint. I do not have a constraint directly in terms of fatigue life available, but with these back calculations, I can come back to this geometry now, perform a mass optimization, and put up a constraint on stress that, okay, do a mass optimization such that the stress doesn't go beyond 80 megapascal. Okay, and then ultimately the design you get, you can perform a validation, make sure that the stresses are within 80 megapascal, and from that validation study, if you perform a fatigue analysis, definitely if the stresses were less than 80 megapascal, we'll get a fatigue life of what we want to do. Okay, so we have not audible. What about metal matrix composites? Again from Arun. Arun, I really am not the best person to answer this question, but we do have those ACP modules available with this. I'm hopeful that these things, these kind of metals can be uh, dealt with using ACP. Why don't you reach out to us through a support request maybe, and we'll be glad to help you with that. If you can model this too, can we get the recording? Do we get any material on soft form? Okay, why is the typical time required to complete this design validation of lightweight product? Some questions from Suraj. Okay, maybe I'll take Suraj's question later. In topology optimization by lattice structures for additive manufacture, what about loss of safety margin? Heavy commercial vehicle are overloaded to up to 150 to 100% in India. This remains an interesting question coming from field. See, the factor of safety becomes important. The kind of example I shared with you, the bracket example. So initially, I think the stresses were around 20 megapascal and my allowable limit was, let us say, 200 megapascal. I went all the way up to 190 megapascal. Now, what this application is all about plays an important role. For the bracket example, it might be having a role, the bracket might have been installed in a pump with no lives involved. So I was okay with that sort of a study where the factor of safety just turned out to be 1.09 or 1.2. But if it finds an application in an automotive vehicle or a truck, then definitely we have to have a higher margin of factor of safety. Again, it boils down to what I want. Ideally, a factor of safety of 1 is what says that would work for you, but based on the kind of application where are human lives involved or not, if human lives are involved, we may want to get a factor of safety of 5. Now the question is, what is the factor of safety of your existing design? If your existing design is having a factor of safety of 10, it again, it's a question that is a subjective question. Do we think this is over designed, or do we still feel there's a scope of mass reduction? So when the human lives are involved, we may want to bring the factor of safety down from 10 to 5. This is the scope we have in terms of optimization. If human lives are not involved, we want to bring that down from 10 to 2, let us say. But if the factor of safety is already 5 for a very critical application, that means your design is just functioning well. We cannot go through a topology optimization route to design it further to remove any further mass, because that may have a adverse effect on the factor of safety, which is just on the critical range. If the allowable critical range is 5 and we are having 5.5, that should not be the case for topology optimization.
Thank you.
Shaman.
That's in the chat box. So I'm also posting few references or articles on lightweighting for the participants. You could check into that. You would have a couple of collaterals or articles on vehicle lightweighting that will be really helpful for you later. Also, you could take those references. And if not any more questions, we'll gladly close the session after a wonderful presentation and a Q&A. So if there's no any more questions, we'll close it off. So this is your last chance on any question and answers. If you want to unmute yourself, you can unmute and ask right away, or just pop it up in the chat box. Okay, then thank you all for attending. We'll close this session. Thank you, Gaurav, once again. We'll definitely have you as a speaker, maybe in another webinar. So we'll catch up with you soon there. And thank you all attendees for joining today's webinar on vehicle lightweighting. Hope you had a wonderful session and informative session as well. If you do want to know more about this, you could definitely reach out to ANSYS. They'll be really glad to help you out. And until then, this is Suraj from my senior signing off. Let's meet you in another webinar. So thank you all. Have a great day.
Thank you, Suraj. Thanks, everyone.
Thank you, Gaurav and you see.